All right, so we've got a hula hoop rolling down a hill. And nothing about this problem is too difficult, but it involves the newest stuff that we covered. So that may have tripped some of you up. We will see. The question text goes as follows. A hula hoop with a radius of 0.5 meters is carefully balanced and then allowed to roll without slipping down a hill. It starts from rest, has an angular acceleration of 2 rads per second, in other words, rads per second squared, and travels 30 meters along the slope before coming to the bottom of the hill. Okay, so 30 meters along the slope is this part. We'll call that delta x, and delta x is 30 meters along the slope. I guess it levels out after that. Okay. How many revolutions does the hoop make before reaching the bottom of the hill? All right, so how many revs? All right, well, because we know it is rolling without slipping, we know that delta x has to equal the arc length covered along the edge of the hoop. And that, in turn, is equal to the radius of the hoop times its angular displacement. Okay. This only holds if you're rolling without slipping, but we're told we are, so we're okay. And if we look at this, we know everything we need to know, right, to calculate what delta theta is. That's going to be related to the number of revs. So that's delta x over r. So that's 30 meters over 0.5 meters, which gives us 60 rads. Now, of course, we're not asked for radians, we're asked for revolutions. So we need to take that and divide it by 2 pi radians, okay? So in other words, 60 rads is 2 pi rads down here, 1 rev up here for the conversion factor, and that'll cancel rads and give us revs. If you do that, you will get 9.55 revolutions of the hula hoop to cover 30 meters. All right, for part B, go down here. How much time does it take for the hoop to reach the bottom of the hill? All right, so we want the time for our little journey here. And if we want to calculate that out, well, we can try to go straight forward for it. You have a quadratic. You could directly solve that. You could also sidestep around that by solving one of our equations of motion for t. We know this, that's 0. We don't know the final angular velocity, but we do know the angular acceleration. So we just need to go find the final angular velocity of the hula hoop. We have another equation of motion, which will tell us what that is, which is this one. We know all of the quantities in this. This is 0. And we can find that this whole thing is the square root of 240, which is about 15.5 rads per second. We take that, we put it in here, and we should get that time is equal to about 7 3/4 seconds. Lastly, we're asked C, why is it important to specify that the hoop rolls without slipping on the hill? What would change about your calculations in part A if the hoop did slip? You may answer here or in your written work. Okay, so this was the connection. I think I mentioned this earlier. This is the thing that is dependent on rolling without slipping. Because if you do slip, right, imagine that you slip completely, right? Imagine like being on ice in a car and the wheel spinning around and finding no traction. You can cover a lot of arc length without covering any delta x, sort of no progress made for the car or the hula hoop. Okay, and there are various forms of slipping, but the big thing that breaks down is that relationship. So if you roll with slipping, then those two things don't equal. Thus, our calculation wouldn't be accurate. And to know much more whether we would end up with, that being inequality less than or greater than, we would have to know a little bit more about what's going on with this thing, okay? But the basic idea is that that is not the case, so our equations wouldn't be accurate, and it would throw off our answer. It'd be very difficult to calculate, in fact, unless we knew exactly how much it was slipping, for instance, right? Okay, that's that question. We'll move on to the next one.